A way to see the big picture without checking every single little bit.
Mhm.
Well, that's sort of what looking at a ninth degree polynomial can feel like. It just looks incredibly complex.
It really can.
But apparently, with the right tools, it can show some, well, surprisingly neat structures underneath.
Absolutely. And that's really the core of what we try to do here in these deep dives. We've got some interesting source material today. A listener sent in this document, c9.pdf,
Right.
and it gets into several of these ninth degree polynomials. So our mission really is to go beyond just staring at the equations.
Hmm.
We want to understand, their basic properties and ultimately how to find their roots, their solutions.
And it's not about just grinding through the numbers, is it? The source mentions a specific tool for this.
Yes, the discriminant formula of Mourad, Sultan, Ezouidi, H. Dism.
That's the one. So it's like a special magnifying glass, maybe.
Uh-huh.
Helps us see patterns in what looks like just a jumble of
Well,
terms.
precisely. You can think of it that way.
Mm.
And the polynomials we're looking at in the source, they come in slightly different flavors. Some have all the terms, x to the 9, x to the 8, all the way down.
Hmm.
Others look like they might be missing some powers of x. But the neat thing about this discriminative formula is it's designed to handle these different forms and, well, hopefully reveal if there's a simpler structure hidden inside.
Okay, let's jump in then. Starting with the first one from the document. It's px equals. Okay, here we go. Minus by t3 by 820 by 8020 by 92 plus 8020 by 820 by 93 plus I like by 20 by 820 by 93 plus I20 by 820 by 90 by 8020 by 96 6 minus 22 by 820 by 820 by 96 minus O20 by 820 by 96 by 96.
Wow. That's quite a list of coefficients, isn't it?
It really is.
So to make it a bit easier to handle, the source uses a generalized form. It writes px equals minus minus plus 0, and so on, down to minus minus many 20 by 820 by 88 equals 0.
Okay, so the wool sub RQ things are standing in for the actual numbers we just read out.
Exactly, they're placeholders.
Yeah.
So LQ corresponds to the coefficient of S, which was 1 in our example.
Right, because it was minus xi.
Correct. So LQ is 1. Then LQ relates to the exotherm, that LEQ 20 by 820 by 92. And it continues like that all the way down to L0 EQ 20 by 8020 by 80 TQQ, which is that last constant term, 8020 by 820 by 99. Think of them as the ingredients list for this specific polynomial.
Got it. So the main goal is finding the x values that make this whole thing 0, the roots.
Mm-hmm.
And the source says we do this by working out some other values, sub RQ,
Yeah.
which are somehow related to these Euler values we just talked about. And the orange goes from -1 up to 8.
That's the core idea, yes. These S values are derived from the L values using that discriminant formula we mentioned, the Mourad, Sultan, Ezouidi, HESM formula.
Right.
It provides a systematic way to calculate them. The formula itself looks a bit intimidating on paper.
Mm-hmm.
LOQ, NESQ, NOSHO, KIMES, NEOK, NEO1, NEOSHU, NOIAK, NOS1, NEUQK, and these made a word NEOK, NEOQK, and Israeliki. Here, N is the degree, so 9 for us. But basically, it's just a recipe. It tells you how to combine the ill coefficients, our ingredients, in a very specific way.
And the point of this recipe is to reveal something hidden.
Exactly, to reveal these ease values. And the source actually walks through applying this recipe to find SAU, S here, all the way up to 0 by E20 by 820 by 88Q.
And after churning through that formula, what comes out?
Well, for this first polynomial, the result is surprisingly neat. These values are S0, Z0, S0, 0, S0, 0, S0, Z0, 0, S0, 0, S0, 0, so S0 equal to 0, S0 equal 0, S0, AEO, ACRO, EO is E by 820 by 8 by 88, RE6. Lots of zeros there.
Oh, interesting. So what does that do for us? How does knowing these ease values help?
This is where it gets really good, because these ease values let us rewrite our original complicated ninth degree polynomial in a much, much simpler form. It becomes px, it's xeo plus 11x equals 6 equals 0.
Whoa, wait, look at that. Most of the terms just vanished.
They did. The x, all gone. The discriminant formula essentially distilled the polynomial down to its core structure.
It's like it filtered out all the noise. Okay, that's much less scary. So x at minus 6 pi arrow plus 11x arrow minus 6 equals 0. How do we find the roots of this?
The source suggests a really neat trick here. Notice the powers. 9, 6, 3. They're all multiples of 3.
Ah, all right.
So let's make a substitution. Let's say a new variable, capital X, is equal to x.
Okay.
If we substitute x for x everywhere, what do we get? We get x minus 6x arrow plus 11x minus 6 equals 0.
That's just a cubic equation in capital X.
Exactly. And solving cubic equations, while not trivial, is something mathematicians have known how to do for centuries. It's a standard form.
And does the source tell us the solutions for this cubic in X?
It does. For this specific one, x8, xxx, plus 11x zero, the roots are nice and simple. X is 1, x is 2, and x is 3.
Okay, great. But those are the values for capital X. We need the values for the original little x.
Right. And remember our substitution. X
Yeah.
is x zero. So to get back to x, we need to take the cube root of our x values.
So x is the cube root of 1, or the cube root of 2, or the cube root of 3.
Almost. Here's a key thing, especially when we're dealing with polynomials. We usually need to think about complex numbers. Every non-zero number actually has 3 distinct cube roots in the complex plane.
Oh, right. Okay. Not just the one real root we usually think of.
Exactly. So for each of x1, x2, and x3, we need to find all 3 of its complex cube roots. The formula for this involves complex exponentials. It's given as xk is in the set 0, 1, 2 and equals the cube root of x times e to the power of 2, 3.
Okay, so that k taking values 0, 1, and 2 gives us the 3 different roots for each value of x.
Precisely. So since we had 3 values for x and each gives 3 cube roots, we end up with 3 times 3 equals 9 roots for x in total, which makes sense for a 9th degree polynomial.
That fits perfectly, and the source also connects these x roots back to the original coefficients using something called alphac.
Yes, it shows a relationship alphac equals L cubed plus xk9. It even gives examples for k0 for each of the x1, 2, 3 cases. It's showing how the initial L ingredients are still fundamentally linked to the final x solutions via this alpha value.
Huh. It really ties it all together. Okay, that first polynomial makes a lot more sense now. What about the second one?
Right, let's look at polynomial number 2. Px. Ojo plus lanya plus ogre dono plus ajo podio o plus anya o yeah plus meyo oikia e.
Okay, this one looks like it has all the terms again, from x yo down to the constant. And the coefficients are pretty big integers.
They are, and again, the source lists the corresponding OQ's values. OQ is 18 this time, OQ is 144, and so on, down to all 0 by QU by 820 by 88Q being 513. It looks, if anything, maybe more complicated than the first one.
So do we just apply the same discriminant formula again?
That's the plan. The beauty of having a method like this is its systematic nature. So we take these new OQ's values and feed them into the Mourad, Sultan, Ezouidi formula.
And what pops out for the e's values this time? Another simplification.
A very dramatic simplification, actually. The source shows that when you run the numbers for this polynomial, SIR, SR, SR, SAR, all the way up to 0 by E, 20 by 820 by 87R, they all come out as 0.
All of them, except the last one.
Exactly. Only 0 by E20 by 820 by 80 is non-zero, and it equals 99.
Wow. So if all the other s values are 0, what does the simplified polynomial look like?
It becomes incredibly simple. Px is SR99.
Equals 0.
Just
x minus 99 equals 0.
That's it. Or rearranging slightly,
right.
xx equals 99. All those intermediate terms completely canceled out in NAS calculation.
That's amazing. Talk about revealing a simple structure. So finding the roots here is just finding the 9th roots of 99.
Precisely. Much more direct than the first case. And again, thinking in complex numbers, there will be 9 distinct 9th roots.
Right, 9 solutions.
The formula is similar to before. Xk is in 0, 1, 8, and equals the 9th root of 99 times e to the power of trs. That gives all 9 complex roots.
And I bet there's an alphac connection here too.
You bet. The source shows alphac olapur plus xk9 again. With OQ being 18 this time, it simplifies to alphac 2 plus e to akin. So that connection between the original coefficient OLCO and the roots holds up again.
It's quite elegant how that works consistently. Okay, 2 down. What about the third polynomial? Does it also simplify nicely?
Let's see. The third one is px. OQ plus where loque plus jula plus zulo plus 1 plus 1 OQ plus onyo plus ono plus where or.
Whoa. Okay, this one looks messy. Some coefficients are the same as the last one at the start, but then it goes wild with that x term being 1 and huge positive and negative numbers later on.
Yeah, it definitely looks less structured, doesn't it?
Yeah.
The OQ values listed reflect that LOQ was 18, LOQ 144, LOQ is 672, same as before, but then LOQ is just 1, LOQ is 118, and so on. Very jumbled.
So does the magic formula still work on this beast?
Well, the formula itself can always be applied. The question is whether the result simplifies things nicely. Let's see what the source says for the S values here.
Okay.
It calculates SRR equals 0, SR equals 0, SR equals 0. So far, so good. But then SRER equals 13,220,415.
Ah, not 0.
Not 0. Then SR are all 0. But 0 by 820 by 820 by 87R is a huge number, 683 billion by 820, 482,673. And finally, 0 by 820 by 820 by 88R is 0.
So we didn't get the super simple result like the last one. We have non-zero O's and 0 by 820 by 820 by 87. What does the polynomial look like now?
Using these as values, the polynomial becomes px, x, xs, x0, 13,220,415 by it, plus 683,999,482,603x.
Okay, still ninth degree, but definitely fewer terms than we started with. We only have xr, and x terms.
Degree times. And if a product equals 0, one of the factors must be 0. So either x equals 0
or the big chunk in the parentheses equals 0.
And if a product equals 0, one of the factors must be 0. So either x equals 0
or the big chunk in the parentheses equals 0. So we found one root straight away. X equals 0 is the solution. That's progress.
Definitely. Now we just need to solve the remaining equation. By 13,220,415 far rows plus 683,999,482,673 equals 0.
That's still an 8th degree equation. Looks tough.
It does, but look at the powers again, 8 and 4.
Kind of like the 963 pattern before, but with 840 this time.
Exactly. So we can use a similar substitution. Let's say yxs.
Okay, if yxo, then xs is xos, which is ys. So the equation becomes y 13,220,415 y plus 683,999,482,673 equals 0.
And what kind of equation is that?
It's quadratic, just a quadratic equation in y.
Right. So we calculate the discriminant first before AC. The source does this calculation.
Yes, it calculates the discriminant for this quadratic in y, and it turns out the discriminant is negative, specifically 988,237,265,467.
Negative discriminant. That means the solutions for you are going to be complex numbers, right? Not real number. Correct. The quadratic formula gives us y. 13,220,415 met as the square root of that negative discriminant 2, which simplifies to y 13,220,415 minigs times the square root of 988,237,265,467. So we get two complex values for y.
Okay, so we have two complex solutions for y, but we need x, and we know y equals xo.
Exactly. So for each of those two complex I values, we need to find its fourth roots.
Fourth roots of complex numbers. That sounds complicated.
It involves a bit more complex number arithmetic, yes.
Okay.
Finding roots of complex numbers involves their magnitude and angle using polar form. Each complex number except 0 has 4 distinct fourth roots.
So we have two complex wave values, each gives 4x roots. That's 8 roots plus the x we found earlier.
That makes 9 roots in total. It all fits.
Okay, so even for this messy one, the method helped find one root easily and broke the rest down into solving a quadratic and then finding complex roots. It's still systematic.
It is. The source does mention some numerical approximations later that seem to lead to real numbers, which is a bit confusing based on the negative discriminant we found directly from the coefficients. It's possible there was some simplification or approximation earlier in the source's derivation that we're not seeing, but sticking to the direct calculation gives complex roots for y.
Good point. Stick to the math. And the alphac relationship, does it still hold?
The source implies it still connects back using LUQ 18 again. So alphac 18 plus xk9 would still relate the final x roots to that initial coefficient.
Fascinating. Okay, one polynomial left in the source. What's the fourth one?
The last one presented is px 94 yum plus 106 yoran plus 84 yum plus 106 hana plus 176 hundreds plus 84 plus 84.
This one has a mix. Integer coefficients at the start, then that minus x term, and then fractions for the x and constant terms.
Yes, the L key values reflect that. Low key nuv, low key 36, then low key 1, lung 8020 by 82197, could balance eat 7, log of 82119 day, and lep say 2820 by 88, could balance 34999.
So apply the formula one more time. What are the S values here?
Well, the source starts the process. It goes through the calculations for S euro up to is euro. But then when it gets to calculating ses euro by E20 by 80 by 87Q and 7 by E20 by 820 by 88Q for the specific polynomial.
Yes. What happens?
It includes a note. It just says will be explained in V10.
V10, like volume 10. So the analysis isn't finished in this document.
Apparently not. It seems for this fourth polynomial, our deep dive using just this c9.pdf source hits a pause. We have the setup, the L values, the start of the S calculation, but not the complete picture or the final simplified form and roots based on this source alone.
Okay. So it's a bit of a cliffhanger for that one.
It is. And it's actually a good reminder, you know, even with powerful mathematical tools, sometimes problems lead to further questions or require more extensive analysis, maybe even refinements to the methods. It shows math is often an ongoing process.
That makes sense. Well, this has been really illuminating. We journeyed through these rather intimidating ninth degree polynomials.
Who did?
And saw how this specific tool, the discriminant formula of Mourad, Sultan, Ezouidi, Hism, could be used to understand them better, to find structure, and even find their roots.
Yeah, we saw quite a range of outcomes. For the first two, it led to really significant simplifications, allowing us to find all the roots explicitly, although involving complex numbers.
Right. The first one reduced to a cubic. The second one almost entirely vanished, leaving x UV's 99.
Exactly. And the third one, while Messier, still yielded one root immediately and reduced the rest to a solvable, though complex, problem involving a quadratic and fourth roots.
And the fourth one, well, it showed us that sometimes the exploration continues.
Mm-hmm. It really drives home the point that even things that look incredibly complex, mathematically speaking, can often be approached systematically. With the right analytical tools, you can peel back the layers.
It makes you wonder, doesn't it? So, for you listening, think about this. Where else might this kind of approach apply? Are there complex systems or problems in your own field, things that seem chaotic, that might have an underlying structure, a kind of solution waiting to be found if you had the right discriminant formula to analyze them?
That's a great question. What kind of hidden patterns could be revealed in other domains using analogous systematic approaches?
Definitely something to ponder.